Hi everybody, my name is Rachel Smith and today I'll be speaking about spherical agglomeration, and particularly we're going to be looking at spherical agglomeration for the pharmaceutical industry, um, and developing mechanistic understanding for process design. So for those of you who aren't familiar with spherical agglomeration, basically it's a process of in suspension or in slurry agglomeration. So most of us are familiar with granulation in so more dry style granulation in high shear granulators, for example, or field bed granulators, where you have particles that you add a liquid binder to. This is similar, but the particles are suspended in a liquid first. So you can see on the left here we have basically in this instance, the crystallizer, and it's filled with a suspension of crystals that have been pre-crystallized already. And our aim is to agglomerate those particles together using an immiscible binder to give us the type of agglomerates that you can see on the right-hand side of the screen. There's a couple of different ways that this can happen. You can imagine that if the drop is much larger than the particles, then we would have a mechanism called immersion mechanism, which basically means the particles adhere to the outside of the drop to start with, and over time they penetrate inside the drop, and then we can have other things happen, of course, coalescence, for example, or breakage. And then eventually we have our formed, I guess, consolidated agglomerates after some time and some mixing. The other possibility is a mechanism called distribution mechanism. And that's where we have the droplets are much, much smaller than the particles. What happens here is that basically the droplets adhere to the outside of the particles. Particles then come together and form very small little liquid bridges between the particles. And then, of course, over time, again, we can also have breakage, and we can also have things like coalescence between different agglomerates. And in the end, we form spherical agglomerates. You can imagine that if your aim is to try and control the size of agglomerates, you may wish to try and follow the immersion mechanism method because the particle size is largely controlled by the drop size. So if we can reduce the amount of coalescence and reduce the amount of breakage, basically the final particle size is related to the size of the drops as opposed to the distribution mechanism where we may end up with it's more difficult to control the final size of the particles. So one of the very important parameters that have been identified in spherical agglomeration is a thing called the binder-solid ratio, and this is a critical process parameter. And the tricky bit about the binder-solid ratio is that it can vary a lot for different systems. So if we have, there has been different systems where you can see sort of 2 orders of magnitude of the amount of binder that you need to add to the system. Obviously, that's very difficult to predict. One of the main reasons for that is, well, we would say the driving reason for that is about the miscibility of the liquids in each other. So basically, none of the liquids are, or very few liquids are perfectly miscible in each other. There's always some miscibility. And what we need to do is use the ternary phase diagram, as you can see on the right-hand side of the slide here. If we use the ternary phase diagram, we can work out what is our actual volume of binding liquid, and also what is our actual volume of continuous phase or suspended liquid. And from there we can target specific binder-solid ratios. So you can see here on this graph, we have the TBSR, which is what we're calling the true binder-solid ratio, where we actually calculate what is the actual amount of binder once we take into account that miscibility, versus the binder-solid ratio. And you can see for this system, actually the TBSR and the BSR are quite different. We can calculate now, basically, if we calculate the ternary phase diagrams and we do the tie lines, we can now calculate how much binder do we need to add to hit a target amount of true binder in the system. And we also have some good ideas about how much true binder we need based off some very simple calculations on porosity of agglomerates, for example. So that's a nice thing. So that's a design parameter that we kind of have a good handle on now. Once we know the amount of liquid that we need, we then start to think about the kinetics of the process and the final size of the agglomerates. So we've done some mechanistic modeling on immersion nucleation. Immersion nucleation is identified as a key controlling mechanism. And there's been a lot of work done, and this has been published now, to predict the kinetics. So basically, you can picture this, you can picture the immersion nucleation mechanism as occurring. You have a droplet, and it's surrounded by particles that are suspended in liquid. Over time, the particles adhere to the surface of the droplet in stage 2. In stage 3, they slowly immerse themselves inside the binder droplet, and then in stage 4, you have complete immersion. You can imagine that two different systems could be, or two different mechanisms could be limiting here. So one would be, the first would be, how quickly do the particles come to the surface of the droplet? So is the droplet always surrounded by particles? And the second is, how quickly do the droplets immerse themselves inside the binder droplet? And in fact, we've developed a parameter, a new dimensionless number that can describe that to us. And that's down in the bottom right, called the agglomerate nucleation number. So basically, if the agglomerate nucleation number is much, much smaller than 1, we have a collision rate limited regime. If it's much, much higher than 1, we have an immersion rate limited regime. And then, of course, it's an intermediate regime. And we can plot this as you can with all good models. So on the left, we have the collision rate limited model. You'll notice that there's different lines on this, and this is for the batch versus continuous. And the main difference between batch and continuous is the amount, the availability of particles at the surface will be different depending on how you operate in the agglomerator. In the center, we have the immersion rate limited model. And then on the very right, we have the combined model. And basically, this is the model where we know we're always limited by something. So basically, we follow the collision rate limited model up until the transition point, and then we follow the immersion rate limited model after that. So in addition to all this work, we've also been looking at population balance modeling, and many of you will be familiar with that. We're using GPOMs to model this. It's actually based on the model is based on a high shear granulator model, because obviously there are many similarities between spherical agglomeration and high shear granulation, despite there being a very different background fluid, I suppose you could say. The mechanisms of formation can be similar. And we're also looking at doing some sensitivity analysis, and that's work that's ongoing at the moment in the population balance model framework. So all of this work that we've been doing is driving towards developing mechanistic understanding, but what we really want to be able to do is design these processes from either first principles, limited amounts of experimentation, and using modeling. So we want to take away a lot of the art from this process and put a lot more of the science in. So the key goal of the workflow that we're developing at the moment is to deliver targeted particle sizes within specific limits for suspension spherical agglomeration processes. And the aim is to use a model-driven design approach. So we're trying to go with models first to inform the workflow. And obviously that will always require some experiments to parameterize the models and provide us with extra information, but we are trying to develop smart, small-scale experiments to help us understand the information that we need, and just very specifically the information we need, without doing huge numbers of parameterizing experiments. And this is work that's ongoing, and it probably will be for a little while. And that's all. So thank you very much for listening to me today. Just in conclusion, we've been investigating several different approaches to develop mechanistic understanding. We've developed a Truebinder solid ratio, the agglomerate nucleation number, and we're doing some population balance modeling, and we're applying this to develop a workflow. And I'd like to say thank you very much to all of our collaborators whose advice and help has been very invaluable. Thank you.